Hey everybody, it's Jenny from Norman S. Wright. We've got a special episode this week. I'm out at the ABB factory in New Berlin, Wisconsin, and we're going to talk about harmonics. So let's go in. Hey everybody, we're here in the labs at ABB and we're going to talk about harmonics. I've got Louis Hill here from ABB, and so I want to talk about what are harmonics, why are they bad, and what you can do about them. So I'll turn it over to you.
Thanks. So I'd like to start off with a little story about what harmonics actually are. So my daughter used to ride horses, right? So we'd have horses and she'd go run the horses around, and they would get all worked up and sweaty, right? And she'd bring it to the horse trough to get a drink of water. They'd put their head in the water and start drinking the water, and you'd get a bunch of ripples and splashings and just kind of a big mess. Well, harmonics are kind of like that. It's pollution on the electrical system. And if you think about the ripples and the splashing, think of those as harmonics. It's wasted water, wasted energy. It's just a waste in your system. So when we look at harmonic performance of drives, we've got different levels that meet different requirements. So the very first one that we're going to talk about here is the 6 pulse without any impedance, input impedance. So you can see here, we have this waveform here. We've got 2 waveforms here, the voltage waveform and the current waveform. So on the voltage waveform, you can see that we've got this little clipping on the top. That's voltage clipping that happens as voltage distortion, right? That's bad for your electrical network. And also you've got this deep ratted ears, bunny ears as we call them. That's your current distortion. That's the horse gulping the water, right? That's the deep bunny ears tell us that we're sucking a lot of current down at one time, and it's causing our electrical grid to take on and create all these harmonics. So when we look at different opportunities for improvement, the next thing we're going to look at is a drive that has some harmonic mitigation. In this case, it's a DC link choke. So as it gets up to speed here, we're going to see that the voltage waveform is less clipped at the top. It's more sinusoidal, rounded at the top. And you can see that the bunny ears now are less pronounced as well. So we're not gulping as much current off the line. One thing I didn't touch upon is the total harmonic distortion, or the current distortion. When we were running the 6 pulse without the input impedance, we were in the 80 to 90% current distortion. As you can see right now, we're about 35% with the 6 pulse drive with a little bit of impedance. So that's one way to make an improvement. But the best way to make this improvement is by applying our ultra-lower harmonic technologies to your electrical system. So as it comes up to speed here, you can see that now the waveform is it's almost purely a sinusoidal waveform. You can see that the pronounced bunny ears that we had are gone, and now they're no longer gulping. So now let's go back to the horse analogy. Imagine, as weird as it may sound, giving the horse a straw. Right now the horse is taking all the water that he wants, when he wants it, and we're doing the same thing here. You can see that our current distortion is 3% at our drive terminals, and that gives us the performance that we're looking for. So when we look at the whys we need it, we've got a host of reasons why you do need it, but you might see motors tripping on over temperature because they're not on drives and the network is so messed up that another motor that might be running across the line might be overheating because of the voltage distortion. You might see circuit breakers trips. You might see lights flickering from time to time. These are, I'll say, nuisance things that you might be aware of when you're walking through your facility. You might be thinking, I might have a problem. So one of the benefits of the ultra-low harmonic drive is the power factor, right? Unity power factor, you're using the power most efficiently, right? You're not creating waste where you get heat off of cables or excess heat off of transformers and distribution systems. And it also helps in reducing risk in your electrical system. So imagine you have a backup generator, right? If you size it for 6 pulse drives, you'd have to way oversize it to handle all the harmonic distortion. But when you look at the ULH package, you might be able to size it in a way that is more appropriate for the application because you're not creating the harmonic current at all. So these are some things that you should consider when looking at harmonic mitigation in your facility.
It's awesome. Thanks for explaining that to us.
Thank you.
That's an overview on harmonics and what you can do about them. I want to ask Jeff Peck from Norman S. Wright to step in here now and talk about how this affects the mechanical system.
So at Norman S. Wright, as a mechanical representative, we have many product lines that we represent, many trusted manufacturers, and the design team trusts us to provide the most energy efficient solutions for their projects, especially in California. So as we select equipment on projects, whether they're chillers or air handlers or exhaust fans or air handling units, the amount of VFDs on the project start to expand. And now we have more and more nonlinear loads on the building grid. So one of the things we offer as a solution is we can do a harmonic analysis and present a study to the design team in order to determine if we meet IEEE 519 or not. And when we don't, we suggest using the ULH technology in order to reduce that harmonic distortion and meet IEEE 519 requirements.
That's awesome. Thanks, Jeff.
And thanks to everyone for watching today, and don't forget to subscribe to our channel.